So this video is on Year 2 Statistics, Chapter 2, which is on conditional probability, building on the first year probability. So question 1 of this prep practice test is on set notation using Venn diagrams. So in this question, we're expected to describe the region shaded here. You can see that the A and C region is shaded, but the parts which are not inside B. And so we use the notation, the U symbol for union or, and the N symbol for intersection and dash symbol for not. So probably the easiest way of expressing this region here is A or C. Now we have to put brackets around it because just like in mathematical arithmetic expressions, multiplying happens before addition in BODMAS. Likewise with logic, ands happen before ors. So if you want the ors to happen first, you have to put brackets around them. So A or C, that whole region, which is this circle plus this circle. But we also want to have not B. So it's A or C in brackets and not B. So oring is union, which basically means we shade in A plus we shade in C, and then intersection means the overlap. So the overlap of not B, so being outside B and being inside A or C. So that's the expression that I would hope to get. But there are other ways of doing it. So you could, for example, say that we're in A and not B. So that's this region here, where we're in A but we're not in B. Or we're in C and not B. So we're in this region, but not this region. And then the union basically means we shade this one in and we shade the second one in as well. Or we could do it as 3 separate regions. This shaded region here, this shaded region here, and this shaded region here. So the first one is in A and not B and not C. The second one is A and not B and C. So that's the intersection of A and C, but not B. And then the last one is not A, not B, and C, which is this one here. So take your pick, but the first one is probably the simplest. Part B, we want to do the reverse. So with part B, we want to find the region which is given by A and B or C. Because there are no brackets here, this means A and B, which is these 2 regions here, which is the overlap between A and B, or C, which is the region inside C. And all we do is we shade in the whole of C, we shade in the whole of A and B, and then we leave shaded both of them when we OR them together. Okay. Now the A and B and C is shaded twice, but that doesn't matter, okay? Because when we OR things, it's one plus the other plus the bit inside. Okay, question 3. Venn diagram. This is very typical of first year as well, but the added complication here is that we can also do conditional probability. So we have 30 students, 16 of them study maths, 15 study physics, 10 study maths and physics, which means that if you work your way outwards, if 10 study both and 60 study maths, then there must be 6 that study maths but not physics. There must be 5 that study physics but not maths to make the 15. And because there are 30 overall, there must be 9 that don't study maths or physics. So once you've filled in your Venn diagram, hopefully you're good at that from the first year, now we're ready to do conditional probability. So what's the meaning of probability of M, a vertical line P? Well, vertical line means given. It's a form of conditional probability. So this means the probability of M given P. In other words, if we know their student is a physics student, what's the probability now that they're a math student? So what we do is we look at all the physics students, that's 15. How many of those are math students? That's 10. So probability of a physics student also being a math student is 10 out of 15, or 2/3. So the probability of being a math student is 16 out of 30. The probability of being a math student given you're a physics student is 10 out of 15, which changes the probability. Okay. So whenever you see the vertical line, the thing to the right of the vertical line is what you're given. That's the region that you look at. And the one to the left is the one that you want the probability of within that region. Okay, so second, or part C, what's the probability of being a physics student given you're not a math student? So if we now look at the Venn diagram, how many not math students are there? There are 5 and 9. 5 students who study maths, who study physics, but not maths, and there are 9 who don't study maths or physics. So there are 14 students that don't study maths. How many of those study physics? Well, it's 5 out of those 14. So probability of being a physics student who is not a math student is 5/14 from this data. Are M and P independent? Well, one test for independence is that the probability of two events, so two events are independent if and only if, when you multiply the probability of one by the other, you get the probability of the intersection. So all we do here is work out the probability of the intersection, the probability of being a math student and a physics student, which is 10 out of 30, and ask ourselves, is that the same as the probability of being a math student, which is 16 out of 30, multiplied by the probability of being a physics student, which is 15 out of 30. And these multiplied together is 8 out of 30, which is not the same as 10 out of 30. So the probability of being a math student and a physics student are not independent, they are dependent. In other words, knowing that you're a physics student alters the probability of being a math student, or being a math student, knowing that you're a math student alters the probability of being a physics student. Okay. So the probability of being a math student, for example, is 16 out of 30. But if you know that you're a physics student, that alters the probability of being a math student with the new information that you have. Okay, so now let's look at tree diagrams, which are commonly used with conditional probability. So a bag contains 6 counters, 2 red, 4 blue. 2 of the counters are drawn at random, so think of it as drawing the first one and then the second one. So the tree diagram will contain the probability of the first one being red or the first one being blue, and then the second level of the tree diagram is going to be the probability of this second one being red or blue, given that the first one is either red or blue. So you can see the tree diagram naturally contains within it conditional probability. So if the first one is red, that's 2 out of 6. So that means the blue is 4 out of 6. Now, if the first one was a red, the probability that the second one is a red, there are now only 5 counters left. Only one of them is red. So probability that the second one is red, given that the first one is 1/5. Whereas the probability that the second one is red, given the first one was blue, is 2/5, because there are 5 counters left, but now there are 2 reds left because the first one was a blue. And so here, although we write R here and R here, actually this line represents the probability of the first one being red, given the first one was red. This one represents the 2/5, represents the probability the second one is red, given the first one was blue. So you may have used tree diagrams before, but if these probabilities are different, realize that there is conditional probability going on where it's important to know what the first event was. Okay, so let's answer some questions. Well, we've filled in these probabilities, which I hope you can do. Carry on filling them. It is conventional to write at the end the probability of going down a route. So the probability of the first one being red and the second one being red is 2/6 times 1/5, which is 2/30. The probability of the first one being red and the second one being blue is 8/30. First one blue, the second one red is 8/30, and the first one blue and the second one blue is 12/30. And we obtain that by just multiplying the probabilities as we go down the tree diagram in a fashion that you're probably familiar with. Part B, find the probability that 2 counters drawn are the same color. So they could be red, red. So we want the probability of red and red. I've missed out the and here, but that's fine. That's conventional. If you write letters next to each other, that means and. A bit like multiplying in arithmetic. Or the probability of them both being blue. So we add the 2 probabilities because they can't both happen at the same time. So the probability of both being red is 2/30. The probability of both being blue is 12/30. The probability of one or the other is 14/30, which is 7/15. Now find the probability that the second counter is red, given that both counters are the same color. Now, another way of doing conditional probability is if you want the probability of A given B, is you do probability of A and B over probability of B. So probability of the first given the second is probability of the first and the second divided by probability of the second. And that's a formula that you should really memorize and know. So in this case, we do have conditional probability in the tree diagram, but it's not the way around that we want. Okay, so we want the probability the second one is red, given that they're both the same. So it's not that the second one is red given the first is red, or the second one is red given the first is blue, which are on the tree diagram, but the probability the second one is red given they're both the same. So if we use the definition, probability of the first given the second is probability of the first and the second divided by probability of the second, we get the probability that the second one is red and that they're both the same over the probability that they're both the same. Now the probability that they're both the same we did in part B, which is 14/30. The probability that the second one is red and that they're both counters are the same color must mean that the first one is red as well as the second one being red. Okay, they're both the same, and the second one's red means the first one must be red too. So we've been asked the probability that the first one's red and the second one's red, which is probability of RR, which is 2/30. So we're going to get a probability of 2/30 divided by 14/30, which is 2/14, which is 1/7. So if we know that both counters are red, without knowing, sorry, both counters are the same, without knowing which color they are, what is now the probability that the second one is red? In other words, that they were both red. And that is going to be 1/7. So not an easy, intuitive probability to calculate. And this is why conditional probability is a second-year topic. Okay. Part D, a bit more practice. Find the probability the second one is red. Well, probability the second one is red is given here at the end of this root and here at the end of this root. But it isn't 1/5 and it isn't 2/5 because the 1/5 is the probability the second one is red given the first is red, and 2/5 is the probability the second one is red given the first one is blue. So how do we get the probability the second one is red? Well, there are two ways of having the second one being red. It's the probability that the first one is red and the second one is red, or the probability that the first one is blue and the second one is red. So we multiply the root giving us the second red, and we multiply the root giving the second is red by another root, and we add them together. So it's 2/30 when we want the probability of the first one being red and the second one being red, plus 8/30 when we have the first one being blue and the second one being red. And that gives us both ways of getting the second one being red. And so that's 10/30, which is 1/3. Now we have to find the probability that the two counters are the same color given the second one is red. Okay, that's interesting. It's kind of the other way around to what we did in C. And we don't necessarily get the same answer. And in this case, we don't. So how do we do the probability of one thing given another? It's the probability of one and the other divided by the probability of the other. So the probability of that we're given is that the second one is red, and that's we did in D. So that was 1/3 or 10/30. So now we need the probability that the second one is red and they're both the same, which we did in part C, and that was 2/30. So now the probability that they're same given the second one is red is the probability that the first one is red and the second one is red, that they're both the same, divided the probability that the second one is red, which is 10/30. And so we get 2/30 divided 10/30, which is 2/10 or 1/5. And notice the difference between D and E. And also notice the difference between C and E. Okay, I hope that makes sense. Last of all, you need to know about formulas. So you need to know the conditional probability formula. The probability of A given B is probability of A and B divided by the probability of B. But the other thing you need to know is what's sometimes called the OR rule. The probability of A or B is always equal to the probability of A plus the probability of B minus the probability of A and B. And if the A and B are independent, then this can be rewritten as the probability of A times the probability of B. But if they're not, we can't do that. So in this case, we know the probability of A or B is 8. The probability of A is 0.6. The probability of B is 0.4. And we want to calculate the probability of A and B. So we just fill in to this formula all the things we know. 0.8 for the probability of A or B, 0.6 for the probability of A, 0.4 for the probability of B, and we don't know probability of A and B. So that means 0.8 equals 0.6 plus 0.4 minus probability of A and B. Rearranging, we get the probability of A and B is 0.2. Okay, I hope that helps with Statistics Year 2, Chapter 2, Prep Practice Test.